Alright, hello class, my name is Hunter Stoddard and I'm going to be walking you through problem 7-2. I'm going to start off with my icebreaker. So anyway, this is the table that's given to you in the problem. We've got different mediums with acetone and hexane at both 25 degrees Celsius. Now we're given different parameters with the number average molecular weight, the second virial coefficient, and then the intrinsic viscosities in acetone and hexane. So for sample A, we're given 8.5 times 10 to the fourth for the number average molecular weight. The second virial coefficient is 0, and then the intrinsic viscosity is 0.87 in acetone and 1.25 in hexane. And then for sample B, we're not given any information for the number average molecular weight or the second virial coefficient, but we're given the intrinsic viscosity is 1.32 in acetone and 2.05 in hexane. So to make the problem a little simpler, I made a few assumptions. My first assumption is that the osmotic pressure pi is equal to 1.23, or not 1.23, but 123 pascals, and that the relative viscosity is equal to 1.5, and that the second virial coefficient for sample B is also 0. So the problem has asked for two things. The first one is what is the number average molecular weight of sample B? And so for that we're going to use equation 6.35 from page 230, and this is from chapter 6, and also the Huggins equation, which is 7.32 from page 268. So the first step is to find the concentration of sample A. Here we're going to use equation 6.35, which is this, where pi over c all to the 1/2 is equal to R times the temperature divided by the number average molecular weight raised to the 1/2 times 1 plus this A2 is the second virial coefficient, and then the number average molecular weight times the concentration divided by 2. And then the value for R is given here, 8.48 times 10 to the fourth. So we plug in the information for sample A and we solve for a concentration of 0.421. And now we can use this to find K prime from the Huggins equation and then get the concentration of sample B from that. So for sample A, these are the calculations I did where using the Huggins equation is here, where the relative viscosity minus 1 over the concentration is equal to the intrinsic viscosity plus K prime times the intrinsic viscosity squared times the concentration. And then you calculate out to get K prime of 0.997. And then you can plug K back into the Huggins equation and solve for concentration of sample B. So here's the beginning of that. And you simplify to get C, but then I set it up because it's kind of a polynomial. So I use the quadratic equation to solve for C. And so using, this is the quadratic equation here with values of A, B, and C, and for the plus side you get a value of 0.277 grams per deciliter, and for the negative you get a negative 0.04, but you can't have a negative concentration, so we're going to use the 0.277. And you can plug this back into the equation from chapter 6 to get the value of the number average molecular weight for sample B. And here's the first step of that. And simplified down, you get number average molecular weight of sample B is equal to 5.6 times 10 to the fourth. Now for part B, it asks what are the Mark-Howink Saccharada parameters of K prime and A for the acetone and hexane solvents. So we start with the MHS equation from page 270, equation 7.35, where the intrinsic viscosity is equal to capital K prime times the molecular weight raised to the A power. And so we start with our acetone solvent and sample A, where I plugged in the values for the intrinsic viscosity and the molecular weight, and then solved for K prime, which was equal to 0.87 divided by 8.5 times 10 to the fourth raised to the A power. And then I substitute that in for the value with sample B for K prime. And I simplify down where I get 1.52 is equal to 0.659 raised to the A power. And using some of the log math information, we can solve to get A is equal to 1. Then you plug A back in for the K prime equation, which K prime is equal to 0.87 or divided by 8.5 times 10 to the fourth raised to the A power. And you solve and you get K prime is equal to 1.023 times 10 to the negative fifth. Now for the hexane solution, sample A, we do the same thing again. We get K prime is equal to 1.25 divided by 8.5 times 10 to the fourth raised to the A power. And you plug that information in for K prime in sample B, and you simplify that down. 1.64 is equal to 0.659 raised to the A power. And again, value for logs, and you can get A is equal to 1.19. But it's important to note that this is actually outside of the range for A, which is supposed to be between 0.5 and 1, which that's probably a result of some of the assumptions that I made. And you plug that back in to get K prime for the hexane solution, and I got a value of 1.7 times 10 to the negative sixth. So in conclusion, we use the Huggins equation and equation 6.35 to obtain a value of 5.6 times 10 to the fourth for the number average molecular weight of sample B. And then we use the Mark-Howink Saccharada equation to get values of K prime for the acetone solution. We got 1.023 times 10 to the negative fifth. And then in hexane, we got 1.7 times 10 to the negative sixth. And then for A, we got 1 for the acetone and 1.19 for hexane. All right, thank you.